Trigonometric functions describe the relationship between the angles and the sides of a right triangle. So let's go ahead and see how those relationships line up and how we can utilize trigonometric functions to find those missing sides or angles. Looking at this right triangle, we have three sides, a right angle, and then this angle alpha. And I'm going to base a couple of naming conventions off of that angle alpha. The side that alpha is opposite of, we're going to actually just call the opposite side. Then the side that is next to it is going to be called the adjacent side. And then the largest side, or the side that is opposite the right angle here, we're going to call the hypotenuse. You need to be very comfortable with these naming conventions because it is going to be kind of how we label and figure out which trig functions to use. But let's go ahead and really understand what a trig function even is. So let's go ahead and extend out each one of the sides of this right triangle by doubling its length. In geometry, we learned that these two triangles would be similar to each other. Well, that means they have proportional lengths, but that's also pretty easy to see. If I doubled the length, then this side right here is going to be 2a. This side over here is going to be 2b. And this side up here, the hypotenuse, is going to be 2 times c. Well, how does this relate to trigonometric functions? Well, first, let's go ahead and define what those trigonometric functions are. So there's three of them. The first one is called sine, not sin, and it's the sine of an angle of the triangle, and that angle is important because that allows us to identify our opposite, adjacent, and hypotenuse sides, is just equal to the opposite side over the hypotenuse. And then there's two other trig functions. I'll write them down and then talk about them. So the other two trig functions are cosine, which is the ratio of the adjacent side to the hypotenuse, and tangent, which is the ratio of the opposite side to the adjacent side. Now, the reason that this works and the reason that I drew these two triangles up here is that size doesn't matter. The ratios are constant. And the reason for that is if this angle alpha isn't changing, then we're getting these similar triangles, which we know are proportional. So let's use this example here and look at the sine of alpha. And I'm going to show that it doesn't matter which triangle we end up using. So the sine ratio of the smaller triangle is just the opposite side, b, over the hypotenuse, c. And what I was claiming is that the size doesn't matter, so that ratio should remain the same for the larger triangle. Well, with the larger triangle, the opposite side is just going to be 2b, and then the hypotenuse in that case is 2c. Well, 2 divided by 2, I know is just 1. So yeah, I get b over c equals b over c. That's totally true. Now the other thing to explore here is what does happen when you change the angle? Well, I did mention that size didn't matter, but does the angle matter? If you change the angle, will the ratios change? As it turns out, they will. So I'll use an example of two triangles that you've likely seen before. These are special right triangles. One is the isosceles right triangle. And using the Pythagorean theorem, if I know that this side here is 1, this side is 1, and using the Pythagorean theorem, I can get that the hypotenuse is the square root of 2. Another commonly memorized triangle is the 30, 60, 90 triangle. With that triangle, I can go ahead and say that I know that this side, if that side is 1/2, then this side up here is going to be 1, and this side here will be the square root of 3. You can verify that one with the Pythagorean theorem, but those are the ratios for this particular size triangle. So let's go ahead and look at the sine of these two different angles and use that to kind of decide whether or not changing the angle is going to affect the ratio. So now let's go ahead and look at an example, the tangent ratio of both of these triangles and see if changing the angle will affect those ratios. So if I'm using 45 degrees, I can actually pick either one. It won't matter in this case. I've got 45 degrees. That means that 1 is my opposite side. And tangent is opposite over adjacent. So the adjacent side here is also 1. So I just get the tangent of 45 degrees is equal to 1. Well, let's go ahead and pick the 30-degree angle here. And if I do that, then if I'm looking for the tangent of 30 degrees, we're going to get 1/2, the opposite side, over the square root of 3, the adjacent side. Well, clearly those are not equal, which makes sense. If you adjust the angle, these are not similar triangles, and therefore they are not proportional. So what we found here is the angle determines the ratios. And in fact, if you were to actually use 60 degrees, so same triangle but different angle, that actually changes this to the opposite side and this to the adjacent side, meaning that tangent of 60 degrees, even though it comes from the same triangle, is the square root of 3 over 1/2, which is equal to 2 times the square root of 3. So even the same triangle can have different tangent ratios if you use the different angles in it. The key to understanding trigonometric functions is understanding that it's a relationship between an angle and the relative position of the sides to that angle. So by changing an angle, it's going to possibly change the size of the triangle, but even within the same triangle, it can change those ratios because the relative position changes. In the next video, I'll actually show you where these trigonometric functions and their values come from, so stay tuned.